Hello again. So we're looking now in the third lecture on random variables, and this time we'll look at binomial and Poisson random variables. Firstly, we look at the building blocks for Poisson. It's binomial distribution. It's for a binomial, I mean. It's Bernoulli distribution is the first we look at. So here we're looking at a single trial. We only have one trial, so in that single trial, the two values random variable x can take is simply 0 or 1. Probability of x equals 1 is p. Probability of x equals 0 is 1 minus p, where p has to be between 0 and 1. And we write this as x is Bern p, Bern for Bernoulli. The symbol here, the tilde means has the distribution, or is distributed as. Now, because this is such a simple random variable, we can tabulate the values over here as 0 and 1. Probability is 1 minus p for 0 and p for 1. And I can find the mean. It's simply 0 times 1 minus p and 1 times p, and that comes to p. If I find u of x squared, I square that first. So it's 0 squared times 1 minus p and 1 squared times p, and then still comes to p. So the variance of x is the mean, so the squared is e of x squared minus the mean of x squared. So e of x squared is p minus the mean squared. And if I factorize the p out, I get p times 1 takes p. Notice this is bigger than 0 because the p is always bigger than 0 and it's always less than 1. So e of x is p and the variance of x is p times 1 minus p. This is a Bernoulli situation, fairly simple. It can still be useful to model many situations. Examples over here, if I toss a coin once and let the random variable x denote the number of heads, then x is Bernoulli 0.5. Toss a fair coin once and let x be the number of 5s or 6s tossed. Then probability of getting 5s or 6s is a third now. So x is Bernoulli 1/3. Be careful, I've changed the variable here. Now from the die will show me numbers 1 to 6. But I'm looking at the event, I get 5 or 6. That's a single event now. Another example in medicine is that I've got if both parents are carriers for cystic fibrosis, then what they have is the genes, in fact the alleles involved here is A, which is the dominant, or small a, which is the recessive. And so if both parents are carriers, that means they carry the dominant and the recessive gene. Now the children can receive either AA from both parents, or they can have an A from one and the small a from the other parent. If they get both small a, so in this case, the child is safe, doesn't have the disease. In this case, the child is a carrier, but doesn't express the disease. In this case, the child actually has the disease. So in genetics, these kinds of things usually are expressed in what they call a Punnett diagram. So what they have is over here, they have the two parents. You can either get an A from the carrier parent or a small a, and likewise you can get the dominant or the recessive gene. So here you've got the dominant from both parents, and here dominant from one, recessive from the other, and likewise here dominant from one, recessive from the other, and here you've got recessive. So probability of this happening is 0.25. A quarter of the time you have the child has both recessive genes and then expresses the disease cystic fibrosis, which is a very unpleasant disease. And so if I let random variable x denote the event the child is homozygous recessive, then x equals 1 if the child is AA and 0 otherwise. So here x is Bernoulli 0.25 and the mean is 0.3 and the variance is 0.21. That means that about 30% of children from parents, both of parents who are carriers, will have this disease. And this is something to watch out for in that case. Quite a large proportion. Binomial distribution comes from Bernoulli, where I have got now repeated trials of the Bernoulli. So a single toss of a coin is Bernoulli. If I toss the coin 10 times, I've got 10 Bernoulli trials, and that's now binomial. So in this case, what's going on is the common features are I have a fixed number of trials, fixed number n of independent and identical trials, the number is fixed beforehand. And I've got two conditions here. The trials are independent and they are identical. There are two outcomes on any trial, which we call success or failure. Success can be whatever you deem as success. So if I toss a coin and I take a look at the number of heads, for me heads is success. If you toss the same coin and you're looking at tails, for you tails is success. Probability of success is P, and that's fixed throughout because I've assumed the identical trial, so that probability must be fixed. And I then define my random variable X as the number of successes in these trials. So X is binomial. It has the binomial distribution. We write X has the distribution binomial bin, and the two parameters are N, the number of trials, and P, the probability of success. Note in this notation, Bernoulli is the same as binomial, where I only have a single trial, N is equal to 1. So if our probability is for binomial, then it comes from some counting processes. We have to be a bit careful over here. Let me look at the example over here. I'm looking at probability the stock market falls on any given day is 0.3, and I'm looking at 6 trading days, and I want the market falling in any two of those. Now I'm assuming there's independence over here. What happens the next day doesn't depend on the previous days. So here, if I look at this, if F is falling in the market and that it just doesn't fall, then the possibilities are it doesn't fall on any of these 6 days, or falls on the first day, or second day, or third day, or fourth day, or fifth, or sixth, or falls on the first two, or the first and the third, and so on. I can list all these out. Now by independence, if I look at the first one where it's fallen on the first day, then the probability for that is 0.3, and for the remaining ones is 0.7 each. By independence, I multiply them out, I get 0.7 to the 5. So the following observations. True or false can occur on any two of the 6 days. That's the first thing. The second is probability of any of the sequences containing true or false is the same. It's just the 0.3 times 2, the 2 false, and the remaining 4 weren't false, probability 0.7. It doesn't matter how the sequence arises, because of independence, the probability is the same. However, there are very many sequences that can have true or false. As I showed you, we can have the false in the first 2 days, the first and third day, the first and the fourth day, the second and third day, and so on. I'm going to count the number of ways this happens, and then add all those up. So multiply the number of times I'm going to get this in 6 days, and then multiply with the probability. That gives me the probability. So this is a counting situation. So if you haven't seen this before, we'll go through this in some detail. This is combinatorics. What I'm looking at here is the number of ways of selecting R things out of N. In my example, I was looking at the number of ways of selecting 2 days where I get false out of 6. So here, we write this as CNR, combinations NR, or NR this way, as I've got over here. And that's worked out by N factorial over R factorial times N minus R factorial. Where N factorial actually means multiplying the numbers N down to 1. And for this to make sense, we define 0 factorial to be 1. 0 factorial isn't 0 times anything, it's just a definition to make this notation consistent. So for example, if I look at N choose N, if I'm choosing all the N things, well, there's only one way I can do that. If I use my formula, I'll get N factorial, the top one, over the bottom one, and then the difference. The top one, the bottom one, and the difference. This is 0. That comes to 0 factorial, that's equal to 1. Now I've got, of course, these two cancel off, and I get essentially 1 out of this. I can only choose N things out of N in one way. If I choose one thing only, I can choose any one of the N things. That means I must be able to do that in N ways. So if I use my formulas, the top factorial, and the bottom factorial, and the difference. Now if I look at this, the 1 factorial is simply 1. The N factorial is N times everything below that. So it's N times N minus 1 factorial. If you look at this from over here, this is N times, and this lot over here is N minus 1 factorial. So over here, these two cancel off, and I get N. My example of 2 out of 6. So the top factorial, the bottom factorial, and the difference. They have to add to 1, yeah? These two numbers here must add to 1. So if I look at this again, 6 factorial is 6 times 5 times everything below, that's 4 factorial. And so you can see these two cancel off. And so the 2 is just 2 times 1. If I cancel the 2 with the 6, I get 3, that's 15. And you'll find also that 10 choose 2 comes to 45. Now, you can calculate these using a calculator. And I'll see that how that works afterwards. So, example here, in how many ways can 2 stocks be selected from out of 10 for a purchase? So it's essentially 10 choose 2, and we saw that comes to 45. It's 10 factorial over 2 factorial, and the difference 10 minus 2, 8 factorial. If I've got a part-time worker can only work 2 days a week, in how many possible ways can he select a weekly roster, a 5-day weekly roster? There's 5 choose 2, and there's the top factorial, the bottom, and then the difference. That comes to there's 10 possible ways he can choose his roster in the 5-day week. How many ways can I select 2 lab mice for an experiment out of 6? Same thing, 15. So on calculators, there's 2 ways. You'll probably find this button there on the calculator, NCR. So you'd enter the N first, then select the NCR button, and then enter the R, and then you'll get the answer out of that. So try that and get that right. We'll go through this in lectures together. So probabilities for binomial distribution are going to be, first of all, probability x equals k is 0 for negative values of k. There's nothing here. K must be bigger than 0, bigger than or equal to 0. And I can't get more than n trials, if I n successes out of n trials. So probability of x equals k, where k is bigger than equal to n, bigger than n will be 0. I can't get more than n successes. So if I want k successes, k will be 0, 1 up till n. I will get either 0 successes, 1 or up till n successes. And then the remaining n minus k must be failures. So k successes, n failures. And the probability of x taking or having k successes is out of n I choose the number of ways I can get successes. Number of ways I get k successes. And the probability for k successes is p to the power k. And these are my n minus k failures. So I can use the formula, this formula I've got, to calculate binomial probabilities, and we'll do some of those. But these things can be listed in tables, and of course we can always use R for this as well. The cumulative, as we saw, is just summing values up. And so the tables will give you cumulative as well as individual probabilities. We'll see them afterwards. And all that does is it just adds all the values up and gives you the values in the table. So we won't use cumulative very often for adding things up unless they're very small, tiny things. Otherwise, we'll just use the formula for single events. And use tables for R. Here's an example. Probably a child from a heterozygous parents is homozygote recessive AA for cystic fibrosis is 0.25. We assume the children from the same parents inherited this condition independently. So probability that in a family of 6 children, not a very large family by past standards, modern standards maybe, 2 of them are recessive AA, and that means they express the disease. So red random variable x denote the number of children who are AA out of 6. Then x is binomial 6.3, and probability of x equals 2 is 6 choose 2, 0.3 squared, 0.7 to the 4, and you can work it out. Now, I can use R for this calculation, so let me do that. Here's my R command all ready to go. If you look under there, under distributions, you'll find continuous and discrete. We'll go discrete, and here I've got binomial distribution. And here it says quantiles, probabilities, tail or probabilities. I want list probabilities over here. So the number of trials I had here was 6. And the probability of success here was 0.25. Okay. Oops, it says 66. I've got 6 trials, not 66. Oops, what's happened there? Try again. Point 25. And what it does is it gives me the whole table of probabilities. So what I'm going to get is probability of getting 0 successes is 0.177 and so on. 1 success is 0.355. 2 successes is 0.2966. Oh, sorry. I've used an incorrect probability. We have this 0.3 here instead of 0.2. Excuse me. So let me change that to 0.25. And that's a 0.25. And so this will be the 0.75 to the 4. And so the probability here works out to be, from my R commander, that was this one here, 0.2966. Okay, I checked that. Yeah. So, at least one child is AA. So that means probability of X bigger than or equal to 1. Now, the easier way to work it out is to look at the complement. Either at least one child is AA or none are AA. So I can take off from 1 the probability that none are AA. So that's 1 minus 620.25 again to the 0 and 0.75 to the 6. And so that's 1 minus, let me look at R again. So this was probability of 0. 0 was 0.17797. That's 1780 when rounded. And that's going to be 0.8220. So usually you'll find this happening quite often. If I have something like this, I can look at the complement instead. It's either bigger than or equal to 1 or 0. In other words, either some children have it or none have it, and those two add to 1. So to work out at least some have it, I can take off from 1 that none have it. That's a common thing that we often do. Another example over here is probably that a pumpkin blossom produces a fruit is 0.2. Assume that blossoms produce fruit independently of each other. The pumpkin vine has 20 blossoms. Probability that these blossoms produce no pumpkins, exactly 5. So here my random variable X is the number of pumpkins produced by the 20 blossoms. Then X is binomial 20.2. Probability of getting none is 22, 0, 0.2 to the 0, 0.8 to the 20, I get that much. And X equals 5 is 22 is 5, 0.2 to the 5, 0.8 to the 1, 5, and that's that much. So you can look at tables and work it out. We'll see tables and lectures together. At least 5 pumpkins, so that means probability of getting, at least 10 pumpkins bigger than or equal to 10. So again, that's 1 minus probability of X being less than or equal to 10. So I'm going to use R for this. So I go to my R commander. If you remember, when I went to distributions and discrete and binomial, I had the choice of tail probabilities. So the variable value that I want here is 10. So I'll put in 10 here. And the number of trials here is 20. And the probability here is 0.2. So I get probability as 0.9994. In other words, almost surely I will not get at least 10 pumpkins. At most 5 pumpkins, so that means probability of x less than or equal to 5. And so if we look at R again, less than or equal to 5, I'll repeat the process, distributions, discrete, binomial, 10 probabilities. So before I had 10 there, and now I change that to 5. And I get 0.8042. So 80% chance of getting less than or equal to 5. Now in this case, of course, the mean number of pumpkins I'm expecting is NP. That's 20 times 0.2. In other words, I'm expecting only 4 pumpkins out of this. So that means most of the time I'll get around 4. So more than 10 is highly unlikely, as you can see from here. Now, the mean and variance of a binomial, I just alluded to that a while ago. The mean is NP. That makes sense. If I toss a coin 10 times, probability of heads is a half. I expect half of them to be heads. That means 5, NP. The variance is n times p times 1 take p. And so the deviation is its square root. Now we look at how to prove this. It's not so difficult. So the first is we're going to express the binomial distribution as a sum of n Bernoulli trials. So I've got n trials. I've got y1, y2 up till yn, and each of this is either 0 or 1. If I get a success, it's a 1, otherwise it's 0. So the number of successes x is just going to be the sum of these things. Because y is Bernoulli, we know the mean is p and the variance is p times 1 minus p. So the mean of x is going to be the mean of the sum, and we know the sum of the mean of a sum is the sum of the means. So I add all the means up over here, and that's p added n times, I get np out of this. For the variance, a similar thing applies. I've got variance of a sum here. Now, if they're independent, and we'll see this afterwards, if the random variables are dependent, then the variance of a sum is the sum of the variances. So I'm just adding the variances up again, and each of the variances for the Bernoulli is p times 1 minus p. I'm adding them n times. I get np times 1 minus p. So this is our work for the binomial distribution. And I'll leave you to look at this example. We'll do this together in the lectures afterwards. We'll come back to the Poisson in the last lecture. Thank you.